So thank you for coming here again. Okay, Greg. Today, like me, many people feel glad to see him here again. Today's speaker is the Professor Greg Budzban, and who is currently the Dean at the SIUE, the College of Arts and Science, CAS. And he spent years here covering there, you may or may not know, and then including as a department chair. And then I'm so happy to have you this fall colloquium. Oh, so I forgot the, yes, he's talking about the convergence conditions for non-homogeneous Markov chains via random works on groups and semigroups. Please welcome him.
Thanks. Yeah, and thank you very much. Thanks so much for the invitation, and it's so wonderful to be back on campus among old friends. So you may have heard by the rumor mill that I'm actually stepping down as dean for the College of Arts and Sciences this coming summer, and part of the reason I'm stepping down is I'm going to be getting involved in some other projects that are going to involve a great deal more time than one would have as a dean. It turns out that being a dean, there's 21 departments in the College of Arts and Sciences. You know, it's a huge college, and it's relatively relentless. And I didn't want to become completely transform into an administrator. So I felt that was about to happen. At some point there's a phase transition, I think, where you just sort of become an administrator, and I didn't want that to happen. So I'm going to be stepping down. But it turns out this summer, I was as I was thinking about this, I re-picked up a couple of old papers that I had published back in the late '90s, actually, and started thinking about them again, and realized that there was something there that was still, there was a few open problems that were still there. And so I was able to sort of pick them up and think about them again. So I'm not going to be presenting anything new today, but I will be, but basically I'll be talking about possible future directions, okay? And so, for those of you who remember, I do sort of random walks on semigroups, and so if old friends will be able to remember some of these things, I'm sure. So anyway, so let me go ahead and get going, and I'll just introduce just some basic semigroup theory. Okay, so basically what we're going to have is we're going to have S and some binary product, so a set with a product. And it's just all we need it to be is just closed and associative. Okay, and we have ourselves a semigroup. Okay. What are some classic examples? So if you let sigma say just be 0, 1, right? And you look at, say, sigma star, which we could call 0, 1, sort of union 0, 1 squared, union 0, 1 cubed, so forth and so on. And concatenation. So this is just all finite strings of zeros and ones. You put them together by concatenation. And this, in terms of symbolic dynamics, this is a very famous example, right? And so this is a classic semigroup. One we're going to use quite a bit is I'm going to use the notation TS of 1 up to n, and this is going to be the transformation semigroup on n symbols. Okay, so this is going to be the set of F from 1 to n into 1 to n under composition. And we'll use this one quite a bit. A lot of what we're going to do is going to involve just the transformation semigroup on n symbols, okay? And then another one, and we'll connect this, is, you know, S is a finite semigroup. And we'll do, say, P of S is the set of probability measures on S. And under convolution, okay? So what we're going to do is if mu and nu are elements of P of S, then we'll say mu star nu of, say, S is going to be the sum of mu st inverse nu of t, or we're summing over t element of S. And of course we're in a semigroup, so we don't necessarily have inverses, okay? And so what does this mean then? This just means, so st inverse is going to be, say, the set of y such that yt equals s. And so that's the way we're going to define this. So this could be a set of things, right? If this were a group, it would be unique, but it could be a set of things. But under this, the probability measures becomes actually a compact semigroup. And compact under the topology of weak convergence, okay? So it'll be compact under the topology of weak convergence. All right? And so this one we won't actually spend any time on, but this is a classic semigroup. We'll use this transformation semigroup and this quite a bit in what follows, okay?
Is it fair to think of this operation as somehow measuring how far it is from, how far the group action is from measure preserving or something?
Certainly, you could talk about things like this. There's sort of like an ergodic theory kind of thing, but this is really you know, essentially looking at. You'll see in a moment that it's really looking at kind of like a random walk. So think of it as mu is choosing elements from S, and nu is choosing elements from S. And if these were the distributions of two random variables that were independent, okay, then in some sense this is the probability that I would land at S after two such transitions.
Okay.
So it really is, I mean, I think the best interpretation would be something like a random walk. These are the distributions of a random walk, and this is looking at the likelihood of being in a certain element after two such transitions, perhaps. Okay? Yeah. Okay, good. Now, I said that we're going to be using these, this transformation semigroup quite a bit, but we're going to actually be using a particular representation of that most often, and that's this. So if I take, so let's just let F be this guy here. So just a little arrow diagram of a transformation on three symbols. I'm going to say that the matrix representation of that is this, right? And so this is just a little permutation matrix, right? Okay. And there's a 1 for an entry in this matrix in the ijth component if I gets mapped to j by the function. Okay. Right. And so so this is F. This is the matrix of F. This is G, say. And say we don't have to have permutations. We're going to be dealing with semigroups, and so this is the matrix of G. Okay. We're going to use that quite a bit because we're going to be decomposing transition matrices of Markov chains into these guys, and we'll see that in a moment. But what's nice about this that if we do composition of functions in the way it should be, in the direction it should be done, so now I say that somewhat tongue in cheek. If you remember, Birkhoff and MacLean actually in their survey of modern algebra back in the day tried very hard to say that composition should be written in this way, with the inputs coming in from the left and the outputs going in from the right, because of the computer science stuff that was going on in the late 50s, early 60s. They were unable to convince anyone of that. And if Garrett Birkhoff and Saunders MacLean couldn't do it, I'm not going to win, right? I mean, but however, they were correct. Okay, so they were correct. And so thinking of having a function f followed by a function g and composing in this direction, okay? If we do that, then the matrix of f composed with g is in fact the matrix of f times the matrix of g, so it's an isomorphism as opposed to an anti-isomorphism. And so we're gonna definitely do that, okay, for a lot of different reasons. Okay, all right, so semigroups, functions and their matrix representations. And then next what we need to do is think about semigroup algebras and the ideal structure on these semigroups. Okay? All right, so if we have a finite semigroup, or in fact if we have a compact semigroup, and we look at the closed ideals, either the ideals or the closed ideals, then it turns out that the intersection of all those ideals are non-empty. Okay? So if I take two ideals, okay, now recall, there's some grad students here, I don't know how much semigroup stuff that you guys know, but of course, so if you have I times S is contained in I, and S times I is contained in I, right? If we have that, this let's see, so this is always fascinating to me. So this right here, this one, S is contained in I, this is a right ideal. And this is a left ideal. And if a subset is of both a left and right ideal, we call it an ideal. Okay. But in semigroups, we also have zeros. Okay. Right. So something can act like a zero. And so if we have S times Z equals Z, we call that a right zero. And Z times S equals Z, we call that a left zero. And if it's a left and right zero, we call it a zero. I've always thought it fascinating that that a right zero is a left ideal. I don't know why that is. Okay, who decided that this is called a left ideal if I put it on the right, and it acts like an ideal, right? So somehow that became a left ideal. I don't know why. Does anybody know why?
It's an ideal with respect to things coming from its left.
So it's an ideal. So the stuff's coming from. So it's on the right. But here.
No, it's in the middle. I'm always in the middle.
Okay, all right.
I think
there you go. Okay.
We lost our innocence once we started to write in
this way. I think
it
so.
Was a big mistake.
Big mistake. Yeah, it could. Who knows? Anyway, but ideals and zeros will have some of those, and also idempotents, right? A zero obviously is such an element that if I square it, I get it back, and so so if you have E equal E squared, we're going to call that an idempotent. Idempotent. Okay. And we'll put a partial order on the idempotents. Okay, so if you have two idempotents E and F, we'll say that E is less than or equal to F if E acts more like a zero. Okay, so if EF equals FE equals E. Okay, all right, so that's partial order. Going back to these guys, if I take the intersection of all of them, that's not empty, because look, if I take two of them, I1 times I2's got to be in I2, and certainly if they're both ideals, then I2 times I1 has to be in I1, right? So it's got to be in the intersection. Okay, so the products are always in the intersection, and so in a finite set, or again, if it's a compact set, we're looking at closed ideals, then this is non-empty. And it's going to be the minimal ideal, obviously, the intersecting all of them. Okay? And these are going to play a role in what we're going to be doing, because they're a special class of semigroup called completely simple semigroups. And those are really important. And so this right here, clearly it's simple because it's the minimal ideal, it doesn't have anything inside it. Okay, so M is simple. And it's got a primitive idempotent. Primitive idempotent meaning that it's minimal with respect to this partial order. Okay? Now that's only necessary to prove in the compact case. In the finite case, obviously if you have any idempotents, there's going to be a minimal one with respect to this partial order. And so let's just show real quickly that every finite semigroup has in fact an idempotent. Okay, and if we could just show that that a to the k equals a for some a, that's sufficient, right? That'll be enough. Why is that? Because then, if that's true, then I could take a to the k minus 1 and square it, right? And then that's going to be a times, let's see, a times a to the, hold on, what did it, a to the k times a to the k minus 2, right? That'll add up to that. And a to the k is equal to a, so that's a times a to the k minus 2, and that's a to the k minus 1. Okay, so all I need to do is show that I have that for something, okay? And then if I take s to the powers, like this, right, just powers of 2, okay? If it's a finite semigroup, at some point they have to repeat, right? So finite, at some point you gotta repeat something. And so you have s to the 2 to the s equals s to the 2 to the t for some, say, s greater than t. At some point that's gotta happen because it's finite. And then, let's see if we could play with this, if I do this right, so 2s to the 2t equals s to the 2t to the 2 to the s minus t. I think I did my arithmetic correctly. Right? And so, that's got to be true. And then this just becomes a, and this just becomes k.
Isn't this S the same as the S to define the beginning?
Yeah, so this was this s. So
No, I'm saying that in your first slide that you cleared out was.
So this is just this is just this is a small s. I'm sorry. Yeah. So this is an element in s.
Okay.
Okay. This is an element in s, and now I'm squaring an element in s.
So that S means that 1 to n, right?
This s.
Means 1 to n is.
Yeah. So no. So this is just so I have a semigroup. I have a semigroup S, and it's got elements, say S1, S2, up to S of n, say. Okay, and I'm just choosing one of those guys, and that's that S. I'm sorry, yeah, good deal. Okay.
And the other S is just natural number.
And, which, yeah, the other, yeah, right, okay, so we, too many S's, sorry about that, very good, thanks. So let's do n here, right?
Okay.
How about in here, and let's do in there, thanks, yeah.
And
Okay.
it has to be the smallest exceeding t, right? Not just anything. The smallest exceeding t when you have.
Yeah, so we just pick that, yeah. I mean, it actually, I don't think it matters which one, if it's the smallest or not.
Oh, but they don't have it like a double cover?
Yeah, so it would just keep going, as long as there's one such thing, I think. Yeah. Good, sorry, you got too many S's. Okay, so we have an idempotent, and it's simple, and so M simple with a primitive idempotent. And that's the definition of completely simple. Completely simple. Okay. Now luckily with functions, it's easy to figure out what the minimal ideal is. It turns out that they're just the functions of minimal rank. So if you have a semigroup, think of it, when you take the composition of two functions, the rank can only go down, right? It can only be smaller than the smallest of the two functions that you. So it turns out the minimal ideal is just all the functions of smallest rank in whatever transformation semigroup you're working with. Okay? But there's a really great way to construct them. Okay? And this will come into play a little bit later. So let me go ahead and construct one. So if you think about it, in the total transformation semigroup, okay, so the full transformation semigroup, minimal rank means just the constant functions, right? The ones that are mapping of rank 1. And so, if I have, again, transformation semigroup on 1 through n, if I just think of, so that is one of the functions, right? Of minimal rank, and that looks like this, right? And then zeros everywhere else, right? And so, if you think about those collection of functions, all they are is functions that have columns of ones, right? Binary stochastic matrices, columns of ones. That's going to be your minimal ideal. And if you think about the structure of that set, if you call this, clearly I'm notation challenged, and so perhaps would E1 be something like it's an idempotent that's mapping everything to 1. Okay, let's see if I copy that and use that later for a completely different setting. But for right now, let's try this. So this is E1, and then E2 would be the one that maps everything to say 2, right, and so forth and so on. Right? Okay. So the minimal ideal is just going to be, well, E1 union E2, union En, and those are trivially a union of isomorphic groups. Right? Each of these is an idempotent, and so it's a trivial group, right? And obviously they're all isomorphic, they're only singletons. And so in this particular case, it's obvious that it's a union of isomorphic groups, but it turns out that in fact, that's true in general. And that was a significant theorem, that completely simple semigroups are always unions of isomorphic groups. And I think Rees, back in the 20s, was the first person to prove that. So that was a non-trivial result to show that every completely simple semigroup was a union of isomorphic groups. And then there was a product, a particular representation that they showed that you can always do. And so so that gives us a way to construct these things. And again, believe it or not, this is all going to come back to Markov chains. So you may not believe that right now, but it's all going to come back to Markov chains, I promise. And so what we have is this. If I look at a function, What I'm gonna say, pi is the so-called partition. So pi of f is the partition of f, and R of f is the range of f. Okay? The partition being the collection of subsets that get mapped to the same thing. Okay, so for example, if I, do I have any of those arrow diagrams up there? No. So if I look at this, okay, and if this were f, I would say pi of f is equal to this, okay? Because the subset 1, 2 gets mapped to the same thing, subset 3, 4 gets mapped to the same thing, okay? And then of course R of f is equal to 1, 4, okay? All right. So it turns out that the way you create these, exactly the same proof that is used in group theory to show that every group is isomorphic to a transformation, a set of transformations, right? Cayley's theorem. That exact same proof is true, works for semigroups as well. And so every finite semigroup is isomorphic to a transformation semigroup. And so you can create these completely simple semigroups by choosing partitions and ranges in a particular way. Okay? And the way you do it is so that R of f is a cross-section of the partition. And what does that mean? That means that R of f intersection P of I, where this is here, this is maybe P1 and this is P2. I'm sure I've used P's in some other way already, but anyway, so P1 is one of the subsets of pi, and P2 is another subset of pi. And if I take this R and I intersect it, I get a singleton, right? So 1, 4 intersect this gives me 1, 1, 4 intersect this gives me 4. Okay? And if I have a partition, I have a range, and I do that, and each time I intersect with one of the subsets in the partition and I get a singleton, I'm going to say that the range is a cross-section of the singleton. Okay? So okay. And so let me show you another completely simple semigroup. So I'm going to take 1, 2, and 3, 4, and then I'm going to take, say, 1, 1, 4, and 2, 3. And then I'm going to take 1, 4, and what? No, so I don't want 2, 3. So 1, 3. Sorry, 1, 3, and 2, 4. And so then I've got 2, 3. Okay. So if you note that 1, 4 is a cross section of this partition, it's also a cross section of this partition. And 2, 3 is a cross section of this partition, and also a cross section of this partition. Okay. So what I've done is I've sort of set up now a structure which will generate a completely simple semigroup. If I look at the collection of all functions that have this partition and that range. Okay? So for example, here you have, if you don't mind, I'll write the matrix form of them. And so 1, 2 goes to 1, so that's going to be here. And then so 3, 4 goes to 4. Okay, and then here, what I'm going to do is I'll just take the flip of that. Okay, I'll just take the flip of that. So now 1, 2 goes to 4, and 3, 4 goes to 1. and you see that's just a little 2-element group, right? If I multiply these matrices together, it's just a little 2-element group, okay? And in each one of these boxes, there will be a little isomorphic 2-element group. And if you think of all of those 8 matrices, they will actually form a completely simple semigroup, okay? And that every completely simple semigroup, a finite completely simple semigroup can be formed in this way. Okay, they all look like that.
So one of them has to be an identity of this group.
One of them actually, so in fact, this right here, if you look at it, you see right here on the diagonal?
Yeah.
Okay, so that actually is the identity, huh? So it's a local identity. It's not the identity right outside of here, but inside this little group, it's the identity, right? And so each one of these will have an identity that's local to its subset, and so the collection of all those will be a completely simple semigroup, and that's completely general. That construction is completely general. Partitions and ranges so that they're cross sections of each other, and you can set them up. All right? There's a little algorithm you can generate them all. Okay. All right. Very good. All right. Now, as promised, we're finally going to talk about Markov chains. Okay. All right. Okay, as advertised. All right, so so let's start off with the following transition matrix. Okay. All right, so T equals this. Okay, so we have 1/4, 1/4, 1/2, and say 1/2, 0 1/2, and 1/4, 3/4, 0. Okay, so that's a perfectly good transition matrix for a finite state Markov chain, right? And of course, obviously the row sums are 1, and so forth and so on. Okay, all right. Now, what does this have to do with this? Well, these actually, okay, so this is a stochastic matrix, right? I mean, this is a stochastic matrix, and so, Tij, the sum of Tij over j equals 1 for all I, right? So you sum the entries in the rows, you get 1. Well, these are stochastic matrices, right? I mean, so each one of these actually is a binary, so-called binary stochastic matrix. There's just a single 1 in each row, and there is in fact a 1 in each row. All right, so it turns out that functions, the matrix representations of functions on a finite set, are in fact a collection of these, and they're actually the extreme points of a convex set. So if you think about the collection of stochastic matrices of a certain size, the extreme points of those, in a certain strict sense, are going to be these guys, right? The 0, 1 matrices. So they're out on the boundary at vertices in some hyperdimensional space, right? They're going to be at the boundary of the vertices. And all the other ones are going to be inside. And not only that, but a theorem by Birkhoff says that you can actually always decompose these into a convex combination of those 0, 1 stochastic matrices. Okay, so for example, so T, let's see if I can actually do this again. Check my arithmetic, if you wish. So T equals 1/4 this guy. Plus 1/4 this guy. Plus this guy. Okay. All right, so that's one way to decompose this matrix into a convex combination of these 0, 1 stochastic matrices, right? And the thing about a convex combination is in fact that we can think of these coefficients as probabilities, right? They sum to 1, right? They sum to 1, they're non-negative, they sum to 1. And so what I'm going to do is I'm going to now think of those as a probability measure on the set of 0, 1 stochastic matrices. Okay? So now, this right here, I'm going to say, I don't know what it is, so we'll call this, B1, B2, B3. Okay, and I'm going to say mu, I'm going to define a probability measure, mu of B1 equals 1/4, mu of B2 equals 1/4, and mu of B3 equals 1/2. Okay? So I'm actually creating, by virtue of that convex decomposition, I'm creating a probability measure on that set. Alright, okay. And it turns out that I could think of it, if this was a random variable with that probability measure as this distribution, I can actually think of this as the expected value of that, right? I mean, in some sense, this is in the form of an expectation, isn't it? It's like probability times, right? The probability of something times the value of the random variable, right? Okay, so now probability is coming into play because we're going to be able to use these decompositions. Yes, please.
Is this decomposition unique or can
It is a very excellent question. And the answer, unfortunately, is no. Okay? And so, and that complicates life, makes it interesting, but it complicates things. And so, yes, that is not a unique decomposition. In fact, I can do this. I had one prepared just for that question. Okay, so there's another decomposition, right? And in fact, so by no means unique, in fact. Okay, in most cases, many such decompositions.
I would expect it to be maybe a couple of dimensions in some space. I'm not really sure whether to think in F2 dimensions or real dimensions, something like that.
You mean in terms of the number of decompositions?
Yeah.
Yeah. That I actually don't know the answer to that. If there's some bound on the number of such decompositions. I don't know of anything. Philip, I don't know. No, I don't know. Yeah. Philip knows all this stuff. He's just sitting back there very politely, not falling asleep, but he knows all this stuff.
But if you take only the bijective, the matrix, then you must have unique, right?
If it's doubly stochastic,
Okay.
if it's doubly stochastic, there is I think a uniqueness.
Yeah, because they are sort of the basis
Yeah,
in
right.
algebra.
Yeah,
But,
yeah.
the second expression is because you are taking the not bijective.
Yes.
Yeah.
Yeah. Now, in a certain sense, though, think of this, right? If I take something that's say 1/3 everywhere, right? If I think 1/3 everywhere.
Okay.
So in fact, I think you could come up with more than one. Could you come up with more than one decomposition over the permutations?
Yes,
Yeah.
so you have a probability and then must be less than 1.
Yeah, because I could do 1/6 over all the symmetric group, right?
Okay.
Right, and I could do 1/3 over the cyclic group,
I see. Yeah.
right? And so I think,
Must be double-checked. Yeah,
so there must be, so I think
Yeah,
there's
yeah.
some
I-
caveat, right? There's some caveat to that
Yes.
uniqueness, right? There's some caveat to that uniqueness. So.
But these two different processes, do they share something in common? As you think about the two processes, right? And you run them. Something common because they're coming from the same matrix? Is there something?
Well, so that's also a very interesting question, and so the random walks that they generate are completely different,
Yeah.
right? I mean, they're really completely different. but they're tied together by this matrix, right? So good question. And so now, so how are we going to handle this right here? So, well, in one case, what we're going to do is this. What I'm going to do is I'm going to think of now, if I have a non-homogeneous Markov chain, okay? So now, let's say x sub n is a non-homogeneous Markov chain. And say T sub n is the sequence of transition matrices, right? For the non-homogeneous Markov chain. The question is, what can I say about convergence of this chain with respect to the convolution products of these probability measures? Okay, so what I'm going to do is this. Let's just say I'm going to pick one. Doesn't matter which one. I'm going to just pick one. One of these decompositions. So I'm going to decompose these guys. I know I get at least one. And so each one of these is going to have some probability measure associated with it. So from this Markov chain, I get the transition matrices. From the transition matrices, I get a sequence of probability measures. Okay? Now, one direction is nice. If I come up with conditions for the convergence of these probability measures, that assures me that the products of the non-homogeneous Markov chain converge. What do I mean by that? See, here's the deal. I tried to come up with some, like I said, I freely admit that I'm notation challenged. And so let me say, okay, so S is S1, S2, so forth, up to Sn, okay? And so mu and nu are elements of P of S. And so if I take mu1 of S1 plus mu2 of S2 plus mu n of Sn, and so this is really what? This is an element in the semigroup algebra, the real semigroup algebra associated with S, okay? So this is, hold on, no it's not, but now it is, okay? Okay, so in other words, this is just this probability measure that gives me a probability on S1 and then I'm multiplying it times S1. You could think of it as this right here, right? You could think of it as like one of these guys. Okay, so this S1 is a finite semigroup, therefore it's a transformation semigroup, therefore it's a set of matrices, and this is a probability measure on those guys. And so this is just a set of coefficients, set of probability, and then I'm doing this, and so I'm getting something that looks like this. Okay? I'm getting something that looks like that. And so then, so maybe I do a nu 1, S1 times S1, and plus nu 2, S2 times S2, so forth and so on, nu n, Sn times Sn. So I have, now for another probability measure.
This index at mu, like 1, already tells you this is of S1, right? Or do I understand it correctly? Like, because
So
it
this
has
is-
mu 1. It
Yeah,
will
so
not-
this is not, this, I don't know where these are coming
okay.
from. I don't know where these are coming from. Those just came from out of nowhere, and they're meaningless, so. Okay, so in other words, mu is the probability measure, and it's mu of S1 times S1, thank you. Thank you, I admit I'm notation challenge.
So it means that you creating another probability?
So these are two probability measures, and these are matrices,
Right.
and these are probabilities on those matrices. And so for example, this guy could look like this, and this guy could look like this. Okay? All right? So those are, yes?
Is that the something expectation?
So this is in the form of an expectation. Yeah, this is, you know, you can think of it as an expectation. All right? It turns out very nicely that, that if I multiply these two things just like regular, like in the semigroup algebra, just multiply, this times that. I mean, literally just do the math, as they say, right? then it turns out that, that if I multiply those, what do I want to call this? Nah, forget it. I don't know what I call it, but this would be mu star nu of S1 times S1. So in other words, I'll multiply this times this. It really is just isomorphic to the convolution product. So in other words, the regular semigroup algebra product is in fact equivalent to the convolution product. And it would take me a little while to prove that to you, but take my word for it. It's true. And so this is, luckily, it's that, okay? So in fact, if I study convolution products, they tell me about the behavior of these matrix products, these semigroup algebra products. And is it clear that if I have now a sequence of these and these convolution products converge, and remember we're in a finite setting here. So I mean by convergence I mean just regular old convergence in Rn, right? I mean, you know, these are just, this is just the first component of a vector, this is the second component of a vector. You know, I mean this is not, they're not talking about any kind of fancy convergences here. So if these things converge, then I'm going to have a single number here times S1, a single number here times S2, so forth and so on. I'm going to actually have a specific matrix that this whole thing converges to. So the bottom line, the moral of the story, is that conditions for convergence on the convolution products provide conditions for convergence on the Markov chain. Okay? So if I know something about convergence of these products, of these convolution products, they give me results on the convergence of the Markov chain. Okay?
But then, how many probability measures you can define this?
How many
probability measures you can define on the same groups of?
Oh yeah, well I mean yeah, obviously infinite. I mean so right. I mean so it's a compact.
No, the reason I'm asking the other way around won't be more difficult to understand the behavior of this one because those things kind of unknown stuff that, and even you don't know how many probability measures you want to define on that set.
Right.
And then know their relationship.
Right.
And then based on that relationship, eventually find out what's going on here.
Yes.
That won't be.
That other direction is hard.
Yeah.
So if you start off with a non-homogeneous Markov chain, coming up with conditions, in other words, finding the decomposition and then choosing the right one, that's hard. However, if you start with a probability measure and look at a family of transition matrices that are associated with that probability measure, then you get something.
Okay.
And that's what we're going to do. Okay, so what I'm going to do is I'm going to write down this thing. I'm running out of time here, so let me write down something very quickly. Okay, so this is a theorem. So let S be a finite, completely simple semigroup. And mu n, a sequence of probability measures. S. Suppose on the limit of mu n of these are the minimal left ideals. These are the minimal left ideals in the semigroup. So in other words, a completely simple semigroup, these are the minimal left ideals, and I'm saying the limit of this has to converge. That seems like an artificial condition, but in fact, you can show that it's necessary. If the things converge, that has to be true. And for some idempotent, lim inf mu n of e is bounded away from 0. So I have just, I make sure that I have a little bit of mass on one of the idempotents. So there's always, if you think of this as a random walk, there's always some chance for me choosing that idempotent when I'm doing the walk.
So convergence here means that whenever you start, you would come back the same position?
So this right here, this is simply, this produces a sequence of real numbers. So when I say converge here, I mean, if I take the measure of this.
I know, I'm saying the point of view of the random walk.
The point of view of the random walk is this. So that, that if I took these products, because again, you can think of the random walk as some probability measure times an element where that probability represents how likely you are to choose that element. Okay? And what I mean by convergence, I mean the convergence of that. So in other words, those products converge.
So can we think of the position of the matrix where you started and then where you ending, or where you ending up and now cannot take any further walk? Is this the same, or this two is different?
This is, yeah, so convergence would be.
Is it the same as the absorbed point, or
So by convergence, I mean this. Think of the entire semigroup. So think S1, S2, up to Sn. Think of the entire semigroup as a big vector. Okay?
Okay.
All right? And then look at mu1 of S1, mu1 of S2, and so mu n of Sn. So now I'm creating a real vector, right? A vector of real numbers. By convergence, I mean that the products, these products, where this represents how likely I am to land on S1 in the walk, these vectors converge.
You got indices on the mu's again.
But now see, I need those because now it's going to be like this. So in other words, I'm walking. I've got a sequence. I've got a sequence of probability
So
measures.
mu1, mu n.
So there's mu1 S1, and there's mu1. So in other words, mu1. So in other words, this is mu1. So
Okay.
Right. Yeah. Okay. Thank you. Yeah. So this is the first step. Now this represents. That's the next step of the walk, right? And then that's the next step of the walk. Okay. And what I mean by convergence is that this sequence of vectors converge. Okay. All right. Okay. Anyway, this right here implies convergence. And so here's a very simple example, but there are any number of examples that you can come up with. This creates a whole infinite family of Markov chains where we have some results on it. Okay, and so here's one. So T sub k equals, so 1/8 plus R sub k, S sub k, and 7/8 minus R sub k plus S sub k. And this is 1/8 plus R sub k, S sub k, 7/8 minus R sub k, S sub k. And this is 1/8 minus R sub k, 3/4 minus S sub k. And then 1/8. This is just an actual numerical example. Okay. So for example, that's a collection of transition matrices, actually an infinite collection of transition matrices. And all you need is this. You need R sub k to be between 0 and 1/8, and then you need S of k be between 0 and 3/4. And then the constraints, you don't get non-negativity.
There's some equal 1.
Yeah, and they sum to 1, okay. And then the decomposition will satisfy this. And so any collection of transition matrices that satisfy this, if it's a non-homogeneous Markov chain, they'll converge, the products will converge, okay? And so, you could play this game with all of those completely simple semigroups that I put up there, so that you can use these conditions to come up with families of Markov chains where convergence is guaranteed. Okay, and so, but it's hard to actually classify exactly how many. In fact, it has not been done. How many Markov chains, how many families of Markov chains can be written as convex combinations of completely simple semigroups? So the question is, for groups, right? So we know exactly the class of non-homogeneous Markov chains that are convex combinations of permutation matrices. But they are the doubly stochastic matrices. Okay, so for doubly stochastic matrices, you can characterize precisely the family of transition matrices that are convex combinations. They are the doubly stochastic matrices. An interesting open problem would be to do that same thing for completely simple semigroups. So in other words, can you in some sense characterize the set of transition matrices that are the family of transition matrices that are convex combinations of completely simple semigroups? Or perhaps just for a subset of completely simple semigroups. Because if you could do that, then you could get actually convergence theorems for large classes of non-homogeneous Markov chains. And that's what I realized this summer when I was thinking about retirement, was that would be the next thing that I would like to do, is see if I could actually characterize all the completely simple semigroups and the transition matrices that are done that, and then I could apply some theorems that I proved 20 years ago. To get a new class of things that would be interesting to study. So, thank you so much for your attention.
Do you have any other question for Greg?
So those groups, I don't know much about the groups.
Yeah.
So what I'm thinking of the groups, probably they are different from each other from some characteristics.
Yeah.
Can I say this way?
Yeah. Like I said, every completely simple semigroup can be thought of as collections of partitions and collections of ranges.
So can I say this way, that based on some characteristic, I can classify them in different groups?
Yes.
Okay.
Yeah.
So then, if I have this transition matrix, then I can find my groups.
That's the thing is can you say, so for example, if I had a doubly stochastic matrix, right? I know that there is a decomposition in terms of permutation matrices.
The reason I'm asking, I'm looking at the practical point of view.
Yes.
So if I have a data set, if I find something like that, and then if there is any way I do classification problem.
Yes. So my point is this. So for groups, it would be, so there is such a thing, right? I mean, so in other words, if it's doubly stochastic, then I know that there's a decomposition in terms of a group. There is no such classification for completely simple semigroups. So that's what the problem would be. Is there a way you could say, well, it's the set of stochastic matrices that have this property, and if it has this property, something equivalent to say doubly stochastic. If it has this property, you know it can be decomposed into a convex combination of matrices from a completely simple semigroup. Okay, that would be the the golden ring, right? And so because there would be because completely simple semigroups are much more general than groups. You would get a much larger class of non-homogeneous Markov chains. You would know the behavior for, right? Doubly stochastic matrices and non-homogeneous Markov chains associated with them are well understood. But things which are not like that are not well understood. And so what this represents is there a way for us to characterize the set of transition matrices that are convex combinations of completely simple semigroups. And if we can, then that would be a nice advance. Yeah, thanks.
Unless you have other question, and then let's thank Greg again. Yeah, we have a refreshment on the third floor.